All right, segment 5, getting started here. All right, we left off with the first law of thermodynamics. So we were talking about heat capacities, specific heats, then we were talking about heats of reaction, then we were talking about how you calculate heats of reaction, whether it be through constant pressure or constant volume. And now then we actually finished out talking about work being done by the system for pressure volume work. And now we're going to talk about the first law of thermodynamics. So in an isolated system, the change in internal energy is going to have to be constant. So the energy final minus the energy initial has to equal 0. Right? Now that's in an isolated system. That means you can't measure internal energy of anything. So you can measure changes in energy, however. So E is a state function. Now if you recall, what that means is we don't care how it gets from point A to point B. Right? So delta E then would equal the heat plus the work. So the change in energy would be equal to Q plus W, basically the heat input plus the work input. Energy of the system may be transferred as heat or work, but not lost or gained. Okay, hopefully that makes sense. What this is saying is that the energy of the system can be transferred as heat or work, but not lost or gained. Okay? If we monitor heat transfers of all materials involved in all work processes, then we can predict that their sum will be 0. Remember, the internal energy cannot change. That's the first law of thermodynamics. For an isolated system, overall, the energy has to be the same. Some energy transfers will be positive. In other words, we'll have a gain in energy. But some energy transfers are going to be negative, or a loss in energy. Overall, it's got to work out to be exactly the same. By monitoring surroundings, we can predict what is happening to the system. So again, delta E is equal to Q plus work. Q will be positive if heat is absorbed by the system. So if heat goes into the system, Q will be positive. Q is negative when it releases any kind of heat. So if the heat comes out of the system, Q will be negative. If work is done on the system, in other words, if we put the work in, that's going to be a positive. Any work being done by the system will be work coming out. So W will be negative. So for an endothermic reaction, delta E has to equal a positive value, right? That means overall, we're putting energy into the system. For an exothermic, then delta E has to be negative. Now delta E will be independent of the path, so Q and W, so it's not path dependent. So here we have our battery system. If we take a wrench and we just mark the poles over with the wrench, we see that we're going to generate heat, right? The wrench will get hot. Here we have the system do work. We hook up the poles and now we have a fan turn. Okay, so we have a fully charged battery over here and a dead battery over here. Whether it's all heat or whether it's all work, the result will be the same. The chemical energy will get used up. Okay, so it's not path independent. It's not state functions. It's dependent on how the change takes place. Okay, so the discharge of a car battery, path A, we short out with a wrench. All the energy converted to heat, there'll be no work. So delta E then equals Q because W equals 0. For path B, we're going to run the motor. The energy here is converted to work with little heat. So W is a lot larger than Q. So delta E would equal W plus Q. Delta E will be the same for each path. Partitioning between two paths differs. Okay. All right, so a gas releases 3 joules of heat and then performs 12.2 joules of work. What is the change in internal energy of the gas? E equals Q plus W. E equals negative 30.0 joules plus negative 12.2 joules. So summing these up then, we get 15.2 joules. So hopefully that's making sense, right? A gas releases 3 joules of heat. That's going to be negative 3. and then performs 12.2 joules of work. That's going to be negative 12.2. Summing those up, we get negative 15.2. Which of the following is not an expression for the first law of thermodynamics? Energy is conserved. Energy is neither created nor destroyed. The energy of the universe is constant. Energy can be converted from work to heat. The energy of the universe is increasing. Which one of the following is not an expression? And hopefully you come up with E, right? And nothing said about the energy of the universe is increasing. All right, so a reaction contracts by 1.534 liters under a constant pressure of 2.134 atmospheres, while releasing 200.7 joules of heat to the surrounding. What is the change in internal energy of the system? 1 liter atmosphere equals 101.3 joules. All right, so there are our options. Hit pause here and give you a chance to work through it. All right, hopefully you came up with A. Here's how you would do it. So energy is equal to Q plus W. So if we go back into the question, we know we're going to release 20.7 joules of heat. So that's going to be negative 200.7 joules plus whatever work is done. The work here we have to calculate, right? They gave us the pressure and the change in volume. So work is equal to negative P times delta V. So that's going to be negative 2.134 atmospheres times 1.534 liters, okay, which is going to equal 3.274 liter atmospheres. That means we're going to then take 3.274 liter atmospheres times 101.3 joules per 1 liter atmosphere, using the conversion they gave us. That gives us 331.7 joules. So now we're going to plug that back in for our work, right? So E equals Q plus W. We get negative 200.7 joules plus 331.7. That's going to equal 131.0 joules. All right. Now I mentioned the bomb calorimeter earlier, and that's holding constant V. So everything we've looked at so far has been pressure being constant. Now here, for a bomb calorimeter, what we're going to do is we're going to have the bomb. We're going to put the bomb in here. So we're going to pump gas in. So this is to let the gas in under pressure. We'll close that valve off so that this is under pressure now. Then we'll have an electric ignition going on so we can ignite the bomb. We'll put a thermometer in and we'll surround this thing with water and hook up a stir. So the bomb has a gas inside it, a flammable gas. And if it's not a flammable gas, like if we want to do a solid object, remember I said this can be used for food, then what they'll do is they'll put the food sample in and then pump it full of oxygen. Okay? Then once we burn whatever's in here, we'll see how much heat comes off. That heat will dissipate into the water, and then we'll measure that temperature change for the water. Okay? And of course, heavily insulation around the whole thing for the whole box, trying to trap everything inside. So, apparatus for measuring delta E in reactions at constant volume. So here the vessel in the center with rigid walls. There can be no change in the volume now. And I've had the opportunity to work with one of these, and it is a steel container. It's like a steel cylinder. That thing's not going to move at all, right? It's designed to take that explosion. It's not even a real explosion. It's a click and it's over. It's not exciting at all. There's no change in volume, so we know delta V has to equal 0. So P delta V then would equal 0. Okay. It's heavily insulated as a vat, and that's because we're going to be monitoring the water bath. Okay? No heat can escape from that. That's the theory. So delta E is going to be equal to Q minus P delta V. Well, we know that P delta V is 0, so that means delta E equals Q, and we call that QV. So the subscript emphasizes that we're at constant volume. All right, let's look at a practice problem. When 1 gram of olive oil is completely burned in pure oxygen in a bomb calorimeter, the temperature of the water bath increases from 22 to 26.049 C. How many calories are in olive oil per gram? The heat capacity of the calorimeter is 9.032 kilojoules per degree C. So we know delta T, we're going to need that. So delta T is going to be 26.049 minus the 22. That's going to give us 4.049 degrees C. Now, the capacity absorbed, the heat absorbed by the calorimeter will be the capacity times delta T. They told us the capacity is 9.032 kilojoules per degree C, so we'll multiply that out, and we have 36.57 kilojoules. So the Q released by the oil then would be the negative of the calorimeter, so that's going to be negative 36.57. Now, we were told at the beginning that we used a 1 gram sample, so we're going to take negative 36.57, divide by 1 gram. That gives us 1 kcal times 4.184 kilojoules. That gives us 1 food calorie over 1 kcal. Kilojoules will cancel out, kcals will cancel out, and we're told it's negative 8.740 calories per gram of oil. Now, for B, olive oil is almost pure glycerol trioleate. The equation for its combustion is as follows. What is delta E for the combustion of 1 mole of that glycerol trioleate? Assume that the olive oil burned in part A was pure glycerol trioleate. Okay, so in other words, we want to use the negative 8.740 calories per gram of oil. So negative 36.57 kilojoules over 1 gram times 885.4 grams per mole. Grams will cancel out. And now we have kilojoules per mole of oil. All right. A bomb calorimeter has a heat capacity of 2.47 kilojoules per Kelvin. When a 3.74 times 10 to the third mole sample of ethylene was burned in this calorimeter, the temperature increased by 2.14 K. Calculate the energy of combustion for 1 mole of ethylene. All right, so that was your second to pause, get some work done here. Hopefully you came up with negative 1410. So Qcal is equal to C delta T. We're told that C is 2.47 kilojoules per Kelvin. We know we went 2.14 Kelvin, so multiply that out and we get 5.286 kilojoules. Kelvins cancel out. We know that the Q of the ethylene is equal to the negative Q of the cal, so that means it's negative 5.287 kilojoules. We know we used 3.74 times 10 to the negative 3 mole, which gives us negative 1410 kilojoules per mole. All right. Next up is enthalpy. Enthalpy is represented by H. It's the heat of reaction at constant pressure, QP. So enthalpy is equal to the energy plus PV. Now it's very similar to E, but for systems at constant pressure. So now we have P delta V work plus the heat transfer. Enthalpy is a state function. Okay, so enthalpy is related to heat quite often, hence the H, except we're at constant pressure. So delta H then is equal to delta E plus P delta V. So we can plug some stuff in here, right? We know that delta E is going to be the heat of the at constant pressure plus the work plus P delta V. Now remember, if only work is PV work, then W equals negative P delta V. So what happens then? Well, then it becomes QP plus W minus W. In other words, it equals QP. So delta H then is really equal to the heat at constant pressure. So for the enthalpy change, delta H, remember H is a state function, so delta H would equal H final minus H initial. And really what we're looking at is the H of the products minus the H of the reactants. Okay, so we can look up enthalpy values for reactants and products. We can look that up for compounds. The significance of the sign of delta H is it's an endothermic reaction. We know the system is going to absorb energy from the surroundings, which means delta H should be positive. If it's exothermic, then we know that the system is going to lose energy to the surroundings, then delta H will be negative. So if it's exothermic, delta H will be negative. If it's endothermic, delta H will be positive. Now that's going to bring in that coffee cup calorimeter. Very simple design here. What we're going to do is measure QP. Obviously, the pressure remains a constant because this is basically not a container that can expand or contract. Air can come in and out, right? We're going to use 2 coffee cups. We just put them inside of each other. And that way we get 2 layers of styrofoam. We can put our liquid in, put a stir rod in, put a thermometer in. Typically in our lab we use a cardboard cover, and they actually work pretty well even with cardboard. Some people will use styrofoam lids as well, so you can get a styrofoam lid for your styrofoam cup, and you can use that to help insulate it out some more. Again, it's open to the atmosphere, which means our pressure will remain constant. Now, let the heat be exchanged between the reaction and water, and simply measure the change in the temperature of the water inside the cup. So in other words, a lot of times what we'll do is take a metal, we'll heat the metal up, we'll have the coffee cup calorimeter, we'll have water inside the cup, we'll take the hot metal, stick it in the cup, and of course the water is usually at room temperature. It will increase in temperature, the metal will come down in temperature, and they'll meet somewhere a little higher than usually room temperature. Again, it's a pretty good system overall. We get really decent results when we do this in lab. Very little heat loss. Okay? And of course we can calculate heats of reaction by looking at QP equal to C times delta T. So coffee cup calorimetry. When we perform this lab, what we'll do is we'll take NaOH and HCl, we'll mix them together, and of course we get an exothermic reaction. So we'll mix 50 milliliters of 1 molar HCl, 50 milliliters of 1 molar of NaOH. The initial temperature here will be 25.5 degrees C, and we'll find that it's going to heat up to about 32.2 degrees C. The question then becomes, what is delta H in kilojoules per mole of HCl? Assume for these solutions that S, right, specific heat, will be that of water, 4.184 joules per gram degrees C. The density for 1 molar HCl is about 1.02 grams per milliliter. For 1 molar NaOH, it's about 1.04 grams per milliliter. All right, so first thing we'll do is start off with our reaction. NaOH plus HCl goes to NaCl plus H2O. Everything here is 1 to 1, right? So we want to make sure it's balanced because the molar pieces will come into play. Remember, we're looking for kilojoules per mole. All right, so Q absorbed by the solution then would be equal to the mass times the specific heat times delta T. So for HCl then, it'd be 50 milliliters times 1.02 grams per mil. That'll give us 51 grams. For the NaOH, it'd be 50 times 1.04, so it's going to give us 52 grams. The mass then of the final solution is 51 plus 52, or 103. The delta T, since we're going to go up to 32.2, we're starting at 25.5, that's going to give us 6.7 degrees C. So we have our mass for our system is 103, and we have the delta T is going to be 6.7. So Q for the calorimeter then is equal to 103 grams. Again, we're going to allow the specific heat of these materials to be that of water, which is 4.184 joules per gram degrees C. And of course, we change 6.7 degrees C. That gives us 2890 joules. Okay, grams will cancel out, C will cancel out, and that's going to round to a Q cal equaling 2.9 times 10 to the third joules, or if you prefer, 2.9 kilojoules. Q of the reaction will be negative Q of the calorimeter, so negative 2.9 kilojoules. For moles, we have 0.050 liters of HCl solution, 1 mole per liter. Liters cancel out, and we've got 0.05 moles. The heat evolved per mole of HCl then would be delta H is equal to negative 2.9 kilojoules over the 0.05 moles, or negative 58 kilojoules per mole. Again, you might have to go through that again. I know it seems a little fast. Just pull the pieces in and just work your way through it. Okay. Second example, when 50 milliliters of 0.987 molar H2SO4 is added to 25 milliliters of 2 molar NaOH at 25 degrees C in a calorimeter, the temperature of the aqueous solution increases to 33.9. Calculate delta H in kilojoules per mole of the limiting reactant. Assume specific heat of the solution is that of water. The density is also of that of water, and the calorimeter absorbs a negligible amount of heat. All right, so again, the first thing we'll do is write a balanced equation. So we have 2 NaOH plus H2SO4 goes to Na2SO4 plus 2 water. Now determine the heat absorbed by the calorimeter. So we have the mass of the solution would be 25 milliliters plus 50 milliliters. Again, we're assuming that it's 1 gram per milliliter, so that's going to be 75 grams. 75 grams times delta T, which is 33.9 minus the 25, times the specific heat, 4.184. That gives us 2.8 times 10 to the third. Right, we can see grams will cancel out, degrees C will cancel out. That way we're ending in joules. All right, so we have the heat of the calorimeter. Now, remember it says specifically for the limiting reagent. So, determine how many moles for the limiting reagent. So we're going to have 50 milliliters of H2SO4, 1 liter per 1,000 milliliters, times 0.987 moles per liter. Milliliters cancel out, liters cancel out, and we get 0.04935 moles of H2SO4. 0.04935 moles of H2SO4. Remember, it's 2 moles of sodium hydroxide per mole of H2SO4. That gives us 0.0987 moles of NaOH would be needed. We had 25 milliliters of NaOH. Converting that to moles, we get 0.05 moles present. So we needed 0.9, we have we needed 0.09, we have 0.05. So the sodium hydroxide then is the limiting reagent. That means we're going to take our heat, negative 2.8 times 10 to the third. We're going to put that over moles of NaOH, convert the joules to kilojoules, and we get negative 56 kilojoules per mole. All right. A 43.29 gram sample of solid is transferred from boiling water to 152 gram water at 22.5 degrees C in a coffee cup. The temperature of the water rose to 24.3 degrees C. Calculate the specific heat of the solid. So just to give you some insight here, you're going to figure out the water. So you're going to use the same equation twice, once for water, once for the metal, once for the solid. All right, so the first thing we'll do is figure out the heat gained by the water. That heat that was gained by the water was that lost by the metal, by the solid. Give you a few seconds to work that out. Pause here if you need to. Okay, so hopefully you got 0.35 joules per gram degrees C. And here's how we're going to do it. Q is equal to M times S times delta T. Now we want to do this for water first, so we're going to figure out how much heat was gained by the water. We have 152 grams of water. Specific heat of water is 4.184. Temperature change went from 22.5 to 24.3. Grams will cancel out, degrees C cancel out, and we get 1.1 times 10 to the third joules. Now remember, whatever the water gained is what was lost by the sample. So now we're going to take negative 1.1 times 10 to the third. We're going to divide that by 43.29 gram of solid. The temperature change for the solid, remember it started at 99.8. So we're going to have 24.3 minus the 99.8. And that's going to give us the 0.35. Right? All right. Enthalpy changes in chemical reactions. And we're about 23 minutes in, so I think we'll stop here. It's a great place to take a break. So we'll end this segment here, pick up with the next segment looking at how we're going to apply this to actual chemical reactions.